Today we're in 7.2, representations of functions. It's kind of a fancy title for not so difficult of a concept, but it's basically just building on what we learned in 7.1, this whole idea of functions, okay? So we have a function rule, and a function rule is written within the context of a familiar formula. Y equals mx plus b. Okay, so you still have your x and y values here. All right, so y equals mx plus b. We have inputs, those are our x values, and we have outputs, which are our y values. Okay, but it also takes it a step further, and it says that inputs are something that we call an independent variable. An independent variable. Somebody tell me, what do you think it means when something is independent?
By itself.
By itself? Alone, right? Not affected by anything else. Dependent would be the opposite of that, wouldn't it? So how in the world does that relate to x and y, right? Independent and dependent? Here's how. What if I gave you y equals x plus 5? Okay, so I'm still following the format, slope-intercept, and I said, okay, well, pick a value for x. So give me some values that you could plug in for x. 2, 0, 3, what else? 5. Okay, so you agree that at this point, I can assign x any value I want. Would you agree? That's what makes it independent. You can assign whatever value you want to x, but the value for y is dependent on the value that you assign to x. For example, if I say x is going to equal 5, okay? And again, I'm just assigning it a value. That means now that the value for y is dependent on the one I just chose for x. That's why it's independent and dependent. When I plug this in for x, y equals what? 10. Do you all agree if I had chosen a different value for x, my value for y would have been different?
Yes.
Okay? So the value of y is dependent on the value I choose for x. Simple enough? All right, so that's where we get the independent and dependent variables from. In example 1, I'm writing a function rule. Again, fancy word for an equation. I'm writing a function rule for the statement. You should notice something. Actually, I just want you to read through these 4 statements, read through them, and tell me what each one has in common. You should start to see kind of a pattern here. Anybody see a pattern, something that kind of happens the same on each one of the 4 statements? Emma? Output is, over and over. Do you guys remember what value we said stands for the output, x or y? Y. And output is a key word for equals. So what I'm saying is each one of these statements starts with y equals. Remember what I just said in the last slide, that we were working within the framework of y equals mx plus b? That's why all of these will start with y equals. And the same thing applies to your homework. It starts with y equals. All right? So output is, all right? And another thing that's in common is all of them have the word input. Input stands for which variable? X. So there's going to be an x somewhere on the other side also. So now the only thing that I need to piece together is what operation and what number is going to be connected to x. Okay? So 5 less than the input. 5 less than the input. What operation would that be? Addition, subtraction, multiplication, or division? Subtraction, okay? So normally when I have a statement, I would just write it how I read it. So 5 minus x, unless it's less than, fewer than, or more than. If you have the word than, you're actually taking it or adding it to from some other number. That's the only exception here. So instead of it being 5 minus x, I must take 5 from x because of the less than. Okay, so if I told you that, let's say, what number is 5 less than 8? You would take 5 from 8. Okay, so it would be 8 minus 5, not 5 minus 8. All right, so less than, you're taking it from some other number, x minus 5. All right, so let's look at the second one. So the other three, I'm just going to basically write it how I read it. The output is the square of the input. The square. Anybody think they know how I would square the input? How I would square it? Isabel? Exponent. X squared. Y equals x squared. Could I assign x a value, any value? Could I make it a 3? Yeah. And then what's 3 squared? 9. Okay, so you can give x any value, and again, that's independent because you can give it whatever value you want, but then y is dependent on the value you give x. Okay, so that's how it kind of ties together. Y equals x squared. The output is 3 times the input. I want you to try to go ahead and write down, finish this function rule. The output is 3 times the input. Make sure you write it algebraically correct. I've seen a lot of different things today on the multiplication. Wanna raise your hand, Darcy? 3x. No dot, no parentheses, not x3. No, that's not how we write. A number times a variable is 3x, okay? So you might need that refresher. So there it is. Number times a variable, okay? Now, what about 1/4 the input? The output is 1/4 the input. Any of my guys? Anybody know? The output is 1/4 the input. Anybody? Trey? Yep, perfect. Y equals 1/4 x. I saw a lot of division signs on this one. Okay? Why? Because you think 1/4 is dividing, so then I would see a division sign. But remember, the fraction shows division. You don't need another division sign. Okay? It's 1/4 of whatever x is. All right? Now, I'm going to put a little plug in here. We're going to talk more about this tomorrow. But if I were trying to choose a value for x, remember, you can give x whatever value you want. If there's a fraction connected to x, you need to focus on multiples of the denominator for your x values. For example, if you choose, let's say 8 for your x value, if I multiply 1/4 times 8 over 1, what's going to end up happening? Doesn't it cross reduces, and then your y value would be a whole number. You don't want to have to graph, because what we do in this lesson is we're going to graph a couple. You don't want to have to graph a fraction. So if you choose when a fraction is connected to x, and again, this is working kind of ahead a little bit, but when a fraction is connected to x, choose values of x that would make the fraction cancel out. Multiples. Okay? You following what I'm saying? Okay? Don't pick a number like a 3, because now you're going to have 3 4s. Now you're going to have to graph that. Okay? You can choose whatever value you want for x. Example 2. Testing solutions. All right? What is the value? Okay, apparently my change didn't save here. This should say y equals 2x plus 5. When x equals 3. So what's happening now is they're saying, I'm going to give x a value. Independent, I can give it whatever value I want. They could have chosen a different number if they wanted to. They just gave it the value of 3. So when x equals 3, you're going to take that and plug it in for x. Let me ask you this question. The answer is no. Does that make it 23? No, because 2x is showing what operation? Multiplication. So that means when you plug a number in for x, you must multiply those numbers together. Okay? All right, so go ahead and do that. Go ahead and do that and finish solving. Okay, 2 times 3, y equals 2 times 3 plus 5. What's 2 times 3 plus 5, guys?
11.
Y equals 11. All right, what about the next one? Y equals 4 times 5 minus 1. What's 4 times 5? 20 minus 1. Y equals 19. Y equals 19. What about the next one? 10 times 5.
50.
Y equals 50. Seems oddly simple for this far deep into the book, doesn't it? Okay, so example 2 really is building into example 3. Okay, so I gave these problems, I gave them random values. In example 3 now, we're going to talk about taking multiple x values, plugging them into the same function rule in order to make ordered pairs. This is something that we actually have already done. Okay, we just called them linear equations. Now we're calling them linear functions, but they're essentially the same thing. Okay, all right, so here we go. All right, in this table, it gives us 3 input values. Well, can anybody tell me how they came up with the output values? Where did those values come from? I had 1, 2, and 3 for my input values. What do you think they did with those numbers? They plugged them in for x in the function rule. So when you plug in 1 into the equation, what's 1 plus 2? 3. So that's how they got the 3 for the output value. Then when you plug in 2, what's 2 plus 2? 4. What's 3 plus 2? 5. Then they took those numbers and look what it formed. Straight line. That's why we call it a linear function. In section 7.4, we're going to talk about linear functions and nonlinear functions. Sometimes it can be a function, but it's not a straight line. Okay, same thing with equations too, actually. All right, so let's do our own. All right, so now we have a different function rule. Y equals negative 2x plus 1. And we have something that looks familiar. A standard set of values. Remember how we talked about with linear equations that you can really choose any value for x that you want, right? That's why it's the independent variable. But why would you not choose 52, 53, and 54 for your x values? They're big numbers, and you're going to have to graph them, okay? So you don't want to have to graph huge numbers. And another reason is so all of our kind of graphs more or less look the same. It's just a little easier to grade. But again, you can choose whatever input values you want, whatever x values you want. All right? In this case, and I'm going to emphasize this again, I can use the standard set of values because I have a whole number connected to x. If I had the fraction, I would want to choose different x values. We're going to talk about that tomorrow. Okay, so what do you think you're going to do with these input values? What do you think you're going to do with them, guys?
Plug them in.
Plug them in for x into the function rule. Whatever the answer is, that's going to be your output, your y value, and then it makes an ordered pair. All right, so let's do the first one together. The signs are important. This is where I see a lot of mistakes happening on quizzes and tests. What is negative 2 times negative 1?
2.
Positive 2. What's 2 plus 1? 3. So my output is 3. You see that? Negative 2 times negative 1 is positive 2. Positive 2 plus 1 is 3. So my first ordered pair is negative 1, 3. And I plot that point. Left 1, up 3, and I plot my point. Okay, left 1, up 3. I want you to do the next 2. Go ahead and do the next 2. All right, next 2. Plug it in, 0. Oh, that's why I love 0, right? What's negative 2 times 0?
0.
Nothing. Plus 1 is just 1. Okay, so 1, so I have 0, 1. And last one, when I plug in positive 1, what's negative 2 times positive 1? Negative 2 plus 1? Negative 1. Okay, so this one is 1, negative 1. So my last 2 points, I go 0, up 1, over 1, down 1. And then I draw my line. This should be a linear function. And like I said, there is such a thing as nonlinear functions. You get more into that in Algebra 1 versus pre-algebra, but it should be a straight line. All right, now I want to point out a couple things. This is really going to help you on your homework, and hopefully you start making some connections. Okay, look at the graph. Ignore the table for a minute, ignore the equation. Could I look at this graph? This is review. Could I look at this graph, guys, and could I figure out what my slope is? Could I count rise over run between the points? Okay, so let's do that. Start at this second point here. How many does it rise? 1, 2, down, and then over 1. So my slope, would you agree, is negative 2 over 1. And look what's here. It's in the equation. Okay? Now let me ask you this. If you were looking at just the equation, do you guys remember graphing in slope-intercept form? There's something that I could look at in this equation, and I automatically know where the first point goes on my graph. The M and B. The y-intercept, this says that my first point is going to be on a y value of 1. Did I have a point on a y value of 1?
Yes.
I did. And then from that point, could I follow my slope down to over 1 and plot my point and draw my line, and I'm done. So in theory, did I need the table at all? It wasn't a waste of time, I promise, okay? Because the table does show us possibilities, and it also proves that you can choose whatever value you want for x, okay? So there is value there, but do you see the connection to equations? It pretty much is the same thing. It's the same thing, all right? So on your homework tonight, you have questions where it gives you an equation and it gives you a graph and it says match them up. So on number 27, does it match with graph A, graph B, or graph C? So here's how you figure it out. Look at the y-intercept. Do you see how that was a +1? So match it with the graph that passes the y-axis at a value of 1. Okay? So on that section on your homework, we're about to get started on it. On that section on your homework, match up your graphs based on your y-intercepts. Okay? That's the easiest way. Did that make sense at all? Look at the last number in the equation. That tells you where the line crosses the y-axis. All right? Okay, so we are going to stop here. I know we do have one more example, the modeling real life. We're going to stop here. We'll take off number 31 on your homework because that's the modeling real life. We'll do that tomorrow. And I'm also taking off number 8. Okay, so you can cross out number 8 and cross out number 31 and stop on number 30. And that's on the recording. Also, if you need any proof, it's right here in the recording too. All right, that's everything you need to know for today for section 7.2.